Hi everyone, I'm Max. I'm a postdoc at the Institut d'Astrophysique Spatiale in Paris, France. And I was kindly invited by the organizers to tell you about why LSST will be a very big deal for solar system science, and in particular for the small bodies of the solar system. And for those of you who typically work with objects on length scales of parsecs rather than kilometers, I'm going to introduce again why we care so much about the small bodies of the solar system. And we can use this nice illustration to understand this. So here we have on the x-axis the semi-major axis of the solar system, and we see we have our 4 terrestrial planets or 4 giant planets and the 2 main reservoirs of small bodies in the solar system, which are the main belt between Mars and Jupiter and the Kuiper belt in the outer solar system. If we look on the y-axis, we have the time, and up on top we have time zero, which in planetary science is at the stage where the solar system was a protoplanetary disk. And what we see here is that we have this gradient of material. So the young sun is surrounded by a disk of hot dust and matter, and it imparts a thermal gradient on the material. And the thermal gradient is here shown by color code. Red is hot, blue is colder. And what happens now is that the dust will start to coagulate and it will start forming what we call planetesimals, rocks on the size of meters, kilometers. And depending on where they form, they will have a different composition due to the thermal gradient. So on the inside, we say that they're rocky, and on the outside, we can say that they're icy. And so the planetesimals will form, then they will grow bigger through collisions. We have planetary embryos, and finally, we have planets forming. And the first planets to form are the giant planets. And as the giant planets form, they will start interacting with the disk due to the gas and the dust that's present there, and they will start what we call planetary migration. So they will radially migrate in the solar system, and this is much like an elephant in a porcelain shop. When you have the big guys migrating, the small guys, they get pushed around. And so what happens is what we refer to as radial mixing here. The sorted material in the disk becomes radially mixed, becomes displaced, and even becomes ejected from the solar system as the big guys move around. So now we jump to the present time. We don't care too much about the details here. And what we have is now in the main belt, we have rocks of different compositions, even compositions from those which did not form there, but which were later implanted from the outer solar system. And this is why we can use the dynamical and the compositional distribution of small bodies today to learn about the initial conditions and the dynamical evolution of the solar system. And we can use it to answer big questions. For example, why is there water on Earth? Earth formed as a rocky planetesimal, and the water was outside in the solar system. How did it come to Earth? It's a big question, because without water, there's no life. Without life, there's no LSST, and then we're all wasting our time here, right? So, big question. But the bad news is that there's a lot of small bodies. It's a lot of work to map them all, to get the composition. The good news is they are just fantastic for surveys. They are numerous, over 1 million already known, with a diameter of larger than 1 kilometer. They're bright and they're fast. They can move up to several degrees per day, depending on their proximity to Earth. Not given here is the subjective criterion that they're also beautiful to look at. So here on the right, please disregard the rather boring looking Crab Nebula in the background. The real star is this trail here in the middle, which is an unknown asteroid that passed through an exposure of Hubble Space Telescope. And so because they're so great for surveys, the history of small body science is also a history of survey science. And we have been using surveys to intentionally observe asteroids for a long time. I'm giving a list here. It's far from exhaustive. And you can see the effect that it has on the cumulative number of known minor bodies in the solar system, which around the 70s and the 2000s with the big surveys really starts to take off. And I, for one, am really excited to see this graph after LSST. I think it will be very fun to look at. But as many of you in the room will know, it's almost impossible to make a survey that doesn't focus on asteroids, because they're always in the field of view. And so even if they're not the primary science case, we still have a lot of asteroid science in the surveys. And here I'm going to have to focus on Sloan Digital Sky Survey, which was a milestone for asteroid science, even though it was not the primary science case, because it gave us visible colors for several hundreds of thousands of asteroids. And we are in fact able to map the compositional distribution of objects in the main belt at very small sizes. So once again, we don't care too much about the details. We have here the main belt and semi-major axis, and what's shown is the distribution of different compositional classes. The message is it's a mess. And the main belt is a mess due to the dynamical evolution of the solar system. And so in short, we can say that just like the NASA DART mission, surveys have big impacts on small bodies. And the question that we have now is, what about LSST? I can sum it up. LSST will be a very big deal. And I'm going to now go through the different science products that we get from LSST in kind of a temporal fashion for asteroids. And we're going to start with the discoveries and the astrometry that LSST will deliver to us. Any second now. Voila. So the Solar System Science collaboration of LSST calls LSST a small body discovery machine, and they have every right to do so. We're expecting the number of known objects from 1 million to jump to 6 million. Here I'm showing a histogram, different minor body populations, before LSST in gray and then after in white, and the factors, the discovery factors. And we see that especially for the outer solar system, we have very big factors in terms of new objects that we will see. And not only will it discover them, but it will also sample them. We will have an order of increase in observations, in total observations of asteroids. And all of, well, the discoveries, they will happen very early in the survey. This is shown here by the graph in the bottom. We have on the X scale the survey time in years. On the Y scale, we have the cumulative completeness of different asteroid populations. We don't care about the different lines. What we care about is this very steep incline at the very beginning, which will tell us that the discoveries happen early. And LSST will especially peak for the first time-ish into the outer solar system and into the sub-kilometer main belt. Of course, we already know some objects out there, but this will nevertheless really be fairly new territory to explore with LSST. What can we do with the discoveries and the astrometry on their own? We can do a lot. For different populations, I'm giving here a list of things that you could do just with the discoveries alone. And it's mostly tasks that rely on statistics of orbital distributions. So I'm not going to go through all of them. I'm going to focus, for example, near Earth region, the source regions. How do asteroids come into the near Earth space? Where do they come from? That's a very important question, because then we get the meteorites from the near Earth asteroids. So we want to know where they come from. We know that the vast majority comes from the main belt. But within the main belt, there are several regions where orbital interaction with Jupiter can drive an asteroid from being in the main belt into the near Earth space. And depending on which region is the most efficient at this process, we will get asteroids from different compositions. So this is a very important problem that we have. Moving on to the main belt, a big question is the question of families. Asteroid families are the remnants of a large planetesimal that was broken up by a collision. So a parent body that gave rise to a lot of children bodies, thousands of them, and we're looking for them because you can study exactly the composition of these objects, the dynamical distribution. And the way that we identify them is by looking at the orbital distribution, because these objects were all in the same place at some point. And we plot the semi-major axis with 1 over diameter. We get what we refer to as a V shape, and then we look for overdensities in this plot. Clearly, if you have an order of magnitude more objects, this becomes much easier to identify these structures in the main belt. Considering the Kuiper belt objects, as I said, we know some objects out there, and we have an idea that, in fact, that there is more mass in the outer solar system than we have in the main belt. However, we cannot see this. And the way that we model the size-frequency distribution, so how many objects we have in a given size range, is, well, very few we can see directly, but otherwise you look, for example, at the craters on Pluto, and you infer from that way the number of objects that you should have around. And with LSST, we should be able to go into this 10-kilometer size range, at least for the very deep images. Then we have the comets. Some people in the room might consider this the most important science contribution of LSST, which is the identification of the ESO comet interceptor target. any comet that LSST will identify will immediately trigger these follow-up investigations and possibly observations as well. Michael Küppers has a post on that you can have a look at. And then we have the question of how many planets are there actually in the solar system? You might be aware that there's an argument that there is a 9th planet very far out that we have not observed directly, but there is some statistical evidence that it might be there. And the statistical evidence, I'm not an expert in celestial mechanics, so I'm going to summarize it. There's a preferential alignment of orbits of TNOs, of trans-Neptunian objects. But it's very few objects that we have so far. And once again, if we go an order of magnitude further in the number of objects, then we're going to be much better able to confirm or deny this statistical alignment of the orbits and therefore planet 9. So that's just the orbital statistics and the discoveries, and we already have a lot to do. But fortunately, LSST will deliver us even much more. And the next thing that we're going to look at is photometry, which we're going to have available. Voila. Here I'm only looking at single band photometry. I'm going to talk about multi-band photometry a bit later. And I'm going to show you how we use single band photometry to really study asteroids as individual objects. And we can start with the very first photometric point that we have of an asteroid. We can immediately use that to make a size estimate. So to estimate the effective diameter of this asteroid. Granted, if you know nothing else about the asteroid, you should put 50% error bars on this estimate, but nevertheless, you can use it. And then you have this for 5 million objects. So once again, you can make size frequency distributions of the objects in the main belt, for example. We have different models for these. And the thing that we can study with size frequency distributions, for example, is collisional history. So you assume that there was a number n of large planetesimals in the beginning, and that these then collide and erupt. And the question is, how many smaller objects are we going to have? And with LSST, we're going to go here into the 100-meter range for these models to verify. This is the very first photometric measurement. Then we have a night, maybe we have several nights, and we're going to be able to construct the light curve of an asteroid. The magnitude of an asteroid changes on the order of hours due to its rotation. And this depends on the shape of the body and on its spin axis. And some very clever people have figured out the inverse problem to take the light curve of an asteroid and to compute the shape and the spin axis orientation, as I'm showing here for Alemania, to compute this from the light curve. And this is a very interesting result because the shape and the spin axis, they largely dictate the dynamical evolution of the orbit of the asteroid. This has to do with solar irradiation interaction, which will lead to a change in the semi-major axis, and which then can lead to quite dramatic interactions with the giant planets for any given asteroid. So having this, the spin and the size will allow us to predict a bit where these objects will go. It doesn't work for all the light curves, but nevertheless, once again, large numbers, a lot of sampling, LSST will give us lots of shapes. And what if it doesn't work with the light curves? Well, maybe that's because there's an irregularity in the light curve, and we're not actually looking at one object, but maybe we're looking at several of them. If the asteroid has, for example, a satellite, you can see this sometimes in the PSF, if it's a bit extended. You can also see it in the light curve if you have some kind of double period in there. And satellites of asteroids, we expect about 15% of asteroids to have satellites. Once again, we can nicely study with them how satellites form and where asteroids are located that have satellites. Another reason for irregularities in the light curves could be transient mass loss. This is when the asteroid starts to eject a bit of material. I'm not going to focus on it a lot because this will be the topic of the next talk by Jessica Agarwal. Active asteroids, they're called then, they're kind of between asteroids and comets. Here I'm showing the light curve of asteroid Gold, and you can see here this flaring event. And this week I learned that it was actually Ken Smith from the Laser broker who first saw this. So if you sit next to him at the social dinner tonight, that could be fun to talk about. Okay, first light, then we have the nights. Now we're going to have to wait a few months. We're going to have to wait a few months for the asteroid to turn, to orbit the sun. And we take photometry at different phase angles. You might be aware that Just like the moon, asteroids go through different phases. We typically observe them at opposition when they're the brightest, but at larger phase angles, we see less of the illuminated side. And what we do then is we construct the phase curve. So we have the phase angle, the angle between the sun and the Earth as seen from the asteroid, and we record the magnitude here. We have an inverted scale, which is why it seems to get fainter, but it gets brighter towards opposition. And these phase curves, they're very useful because for one, they are the first compositional indicator. The shape of this curve depends on the surface composition. So we can use it as a first proxy for the composition. The second thing that will be vital for LSST is that the phase curves, they are required to make use of multiband photometry of colors, which will be the next thing that we talk about. But first, we can do so much with just single band photometry. I made this list and I was really amazed myself. Colors. Colors are the science product that I am the most excited about for LSST because I study the composition of asteroids and well, colors reveal the surface composition. When we're looking at the visible, here we have the filter transmission curves of LSST, and then here I'm showing two typical spectra of classes of asteroids. And in the visible, we can basically distinguish the slope and the presence or absence of an absorption band, which we associate to silicates. And this way we can say whether an asteroid is silicaceous or carbonaceous, depending on visible colors. And as I told you in the beginning, composition directly relates to the formation location of the object. So this is a very valuable information. Right now we have some 100,000 of colors. LSST, if all goes well, will give us millions of them. However, this will take its time. This will take several years because, as I just said, the magnitude of an asteroid in any given band is a function of rotation, of its phase angle, and other geometric effects, which means it's a function of time. This is shown here on the right-hand side, where I have a phase angle versus reduced magnitude of asteroid Bettina as observed by Atlas. This is over several years, and the important thing here is the vertical spread of these magnitudes. All of these are valid magnitude observations. However, depending on at what time you observe it, you might get a magnitude difference in this band. And so if you want to compute colors, differences of bands, you can only do this if either the magnitudes were acquired near simultaneously, which was the case for SDSS, or if you compute a correction for these photometric effects. Julien Peloton has a poster on this. Very briefly, you need the phase curves to do this. And for that, you need the asteroid to complete some orbits around the sun to sample the set phase curve. And this is why colors will take a while to arrive from LSST. Okay, so we're jumping ahead 5 years. And the slide as well. Any second now. Am I pointing here? Also, I have to point here. I have to point. I thought I'm pointing. Okay, so it took a long time, but now we're in the year 2030, and we have colors. Now, what can we do with them? As Jelko told us yesterday, LSST filter set is like an SDSS, but a bit better, which is good because we have a lot of experience with SDSS colors. We know that with them, we can differentiate the main taxonomic complexes, silicaceous versus carbonaceous for asteroids, but that when you look at more detailed, what type of silicaceous asteroid is it, it will be a bit more complicated because these classes are degenerate in the visible. Once again, I'm showing here different typical spectra of asteroids. The silicaceous ones, they have this band at 1 micron, and here we have the SDSS filters compared to the LSST filters. So we have the degeneracy of some classes in the SDSS filters. However, LSST is SDSS plus the Y filter, which is very interesting because it extends a bit further into the 1 micron absorption feature of asteroids. And I was wondering, what can we then actually do with this Y filter? And it turns out for pyroxene-rich classes, it's actually the effective wavelength of the Z filter and the Y filter is quite symmetric around the pyroxene band center, which means that if we look at asteroids which are primarily pyroxene-rich, it will be difficult to tell them apart. However, if we compare silicaceous pyroxene versus olivine-rich asteroids, which we have the green curve here, for example, versus this redder one here, we are able to tell them apart with this new filter, thanks to the different band centers of these two bands. So this is what the Y filter will bring us. It will give us some resolution of, for example, the silicaceous asteroids. And then to really break the degeneracy, we can make a cross-match with ESO-Euclid, which will at some point deliver us near-infrared colors and also a visible band for hopefully 100,000 asteroids. We can cross-match this with LSST and really get the composition based on photometry for a lot of objects, of a lot of small bodies. Why do we want this? Just to get back to this again, because we want to do a statistical analysis of a lot of bodies. And for example, I was talking about asteroid families first. We're looking at overdensities in orbital space, but we can also make the constraint that all of these objects should have roughly the same composition because they derive from the same planetesimal. So now we're adding a second dimension, completely independent from the orbital one, to our analysis, making it much more robust to identify the families, which is why it's good to have a lot of colors and a lot of data in general. We can also continue this argument for the Kuiper belt, where we have seen a dichotomy in the colors, which seems to correlate with orbital properties for the objects. But once again, we don't have that many objects, so it will just be interesting to have this data for an order of magnitude more objects in the Kuiper belt. Here's my summary. I'm basically adding all the big numbers I gave you. I want to finish with a sentence that I have in my head from LSST, and I attribute it to my thesis advisor, Benoit Kari, who said that LSST will turn on the light in the solar system. I think that's a very nice analogy. Right now it's dark. LSST will flip the switch, and we're going to see things. And in that note, the future is bright. Thank you very much.